elements like boron or carbon plus 2 charge and so on, or whether you go higher in mass to charge state ratio, we can separate easily all the peaks here. You'll notice, for example, the nickel plus plus and the molybdenum plus 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 are very close to each other. This is not even 1/3 of a Dalton, okay? And we can separate that without any problem. Dalton basically is the unit that we use, is the mass unit that we use to characterize the elements. We also have higher elements, like in the 4D range, and even if we go to the tungsten plus plus, for example, 90 and so on, we can easily separate all these peaks. Okay, so we are not constrained by any peak overlap here. There might be at one point some peak overlap, but here, if the peaks are separated, they are separated from peak to background, and you can make a better quantification that way. So now that we have this mass spectrum, we can actually translate that into a 3D volume, because each type of element has a different color. For example, this one, so this for molybdenum, all the red here are molybdenum. So here, when we reconstruct in 3 dimensions the tip, we can actually take some understand with ion maps which phase we have. So this is the full data set here, but if basically I take a 20 nanometer slice, which is basically equivalent to getting a TEM image, basically, we have, if we plot the tantalum, the aluminum, and the titanium ions, we have one phase here, and we have another phase that is cobalt from wedge. Okay, so now we can separate the 2 phases here in that case. We can go a little bit further in the visualization if we really want to see here, this phase here. How can I see it better? Because now it's kind of blurry. I can use the isoconvergent surfaces, and I can also focus only on this. Okay, and I can even think about going to one specific particle that I have here, and get this information, about what is the mass spectrum analysis and what is the composition of this particle. Okay, so here, just this particle has this composition. Okay, so I can be very precise in terms of the analysis that I want to conduct. I can actually, I might want to get more statistics. But this is one particle. One particle might be not enough to get all the information in terms of the composition. So you can get a 1D composition profile. So you take a pipe, and you are going from matrix to particle to matrix, okay? And you have the profile that is generated, okay? And you can see here that it's actually richer in nickel in this particle. Or you can actually take what we call a proximity histogram. That means that you can define a specific threshold for the concentration that you want to display. And from the interface that has been created of this particle, you can interrogate the volume at segments or intervals away from the surface or inside the surface. Okay? And by doing so, you are always perpendicular to the surface, which means that you are not making any error between the matrix and the particle. You are not averaging the error. So now it's actually very clear what is the composition in the matrix, gamma phase, composition in the precipitate, gamma prime phase, and also the extent of the interface. Okay. And then if you actually apply that to all the particles and not one, you have better statistics, and that will allow you to get information such as interfacial excess. Okay, so this tungsten interfacial excess going from 0.9 atomic percent to 1.3 atomic percent, you wouldn't be able to find it if you analyze one particle. However, if you do a summation of all the particles, you'll be able to get this information. Okay, let's talk briefly about the additive manufacturing. Here we wanted to compare laser beam experiment with laser beam experiment with, or deposition with electron beam method for additive manufacturing. And what we could see here is that already visually, when you use the laser beam deposition to compare to the electron beam deposition, you could see already on the FIB image that there's some non-uniformity or non-homogeneity here, but that could be just visual. Okay. The Atom probe actually replicates and confirms here with the IM maps that we do have somehow homogeneity here and somehow non-homogeneity here. But you should not just stop at that. You should actually proceed to a mathematical treatment that actually will confirm whether you have homogeneity or not. And if we do a frequency distribution analysis here, that means a difference between observed data and randomized data. You see that there's no real difference here in the first case, the laser beam deposition. That means that we have randomness. However, in the case of the electron beam deposition, we do have fair deviation between these two data. Okay, so we have confirmation of the non-randomness here. If we go a little bit further and select the electron beam deposition sample, you'll see that something that the TEM could not show is that the precipitates here for Erbium would have on either side here some aluminum deposition. Okay? That you cannot get this information with the control. So if we go further, we can do some profiling and look at really going from outside, so take a pipe that way. We have the aluminum that coats this side of the Erbium particle, the Erbium particle, and aluminum the other side. Okay. So this is something that is an insight that we can provide to the researchers in additive manufacturing when they want to use that type of process to do their development. We can talk about additive devices. So additive devices, what we've done is that we went to Best Buy. We purchased an additive device and we deprocessed it. Okay, and we wanted to analyze it with the Atom probe. So what we've done is that we use the FIB to prepare the sample, but the real difficulty is that we could have some defects, and we wanted to really check the information about the interface for the film, the composition, uniformity, and so on. So what we've done is that if you are using this system and do an analysis here, we have about 49% for gallium and nitride, and then you have impurities. So you have indium, aluminum, magnesium. Okay, and those bits are really well defined here. Now, if we go and proceed to the 3D reconstruction, we do have, if we plot 4 to 5 elements here, or ions, we have different regions that we can identify. So we have the gallium nitride, which is everywhere. Okay. But we also do have the indium-rich quantum well region. We do have the indium-based superlattice. So you have about here 21 layers here that I'll show you that we can actually characterize with Atom probe. We have the aluminum-rich blocking layer, or EBL, and you have here a magnesium doping region, okay, for the p-type. So if we take all these ion maps and put them together, it gives you that. So this is basically the image of your LED system. Okay. So you can take a pipe from the top to the bottom and then do a wide decomposition profile. So when you do that, you have the magnesium doping here, you have the aluminum blocking layer here, and you have the aluminum information here. You do have the indium-based quantum wells, 1, 2, 3, 4, 5 here, and you have the indium-based superlattice where you have the 21 layers or lattices here. Okay. So we could focus, and unfortunately we don't have time to show everything. So we could focus on each of these different parts we're going to just focus here on the magnesium dot region. Okay, so we're going to take a square or rectangle, or in the volume, it's actually that we take here, and we're going to see that by interrogating with the mass spectrum and getting an analysis of the composition. We have about a concentration of magnesium here that is about 5 times what we found in the overall data set. Okay, we had about 0.1 something, and now we have 0.07. So the magnesium here on top of that doesn't seem to be randomly distributed. Okay, if you look at here, you have pockets where you have more magnesium than somewhere else. So we can use, for better visualization, one atomic concentration surface for the magnesium, so that you see better these pockets. Okay? And you can analyze these clusters either using the isoconcentration surfaces or using a more sophisticated nearest neighbor statistical method. So you have these isosurface. We could get information about how many particles are there. There's about 32 particles, more than 1% of magnesium, and you can get information about the maximum concentration that you reach with these particles, about 10%. And you can go further by getting information about the interfacial area distribution and the particle volume distribution. That means to be able to say how many particles have a mean interfacial area. Here is 54 nanometers square, and the mean volume. Okay. You can do an experiment or an analysis inside and outside the particle as well. And when you do so, you'll be able to get information such as the magnesium. Most of the magnesium concentration in this device is actually in the clusters, which is not good, because when you want to actually have some carrier activity for the LED, you don't want this magnesium to be located in this magnesium pocket. So it gives information to the manufacturer, for example, on the process of this cluster formation, to be able to get a material that is better functioning. And this is just to show you that the bottom layer here with the Indium superlattice, you could get here between 3 nanometers and 35 nanometers. You have these 21 layers that you can actually easily characterize. Okay? So they are about 1.5 nanometers per superlattice. Okay, let's talk about fiber optics. That also could vary with the material. If you are working with a silicate-based system, or if you are working with a chalcogenide-based system, for example, the conditions for the preparation and for the analysis would be different. Okay? So right now, what I've done is that I was personally involved with this project because one of my friends told me, hey, I'm working on developing some silicate-based glasses because I want to create some optical amplifiers. And by doing so, I have to incorporate magnesium, phosphorus, germanium, and erbium to be able to create some dielectric nanoparticles. And especially what I'm interested in is the erbium. Where is the erbium going? Because the erbium is the rare earth material that will actually confer the spectroscopic properties, optical properties to the system. So in order to help the glass technologies tailor their material, we needed to actually see where the erbium would go. So we started with the NanoSIMS analysis, which is another technique that is manufactured by CAMECA, but that I've used extensively, so I could confidently use it. And if we image here different elements such as silicon, phosphorus, and sometimes molecules such as magnesium oxide, carbon oxide, and so on, you could actually see the position of the dielectric nanoparticles. Okay, so UV road 1.7 nanometer by 1.7 nanometer. So it's a very slow spectral process, but it's also very powerful, especially in the Z direction, because it's a 50 nanometer beam that you use to do the raster. So you have this visual information. Now, can we get a little bit more specific in terms of the numbers? If I try to do a quantitative analysis with NanoSIMS, it will be problematic because the NanoSIMS relies on standards. Okay? You need to have standards to be able to say, okay, I have that much of this element in my system. So we could only do something that was more like qualitative, or I would say semi-quantitative, but that's all we could get at best. So if you take, for example, this plane here, where you have especially this particle that you focus on, and you go in the depth direction, you could see that you are eroding a particle that was at the surface, and there's another big particle that is below, between 250 and 350 nanometers deep down in the material. Now the question would be, for example, what is this? Is this statistically a small particle, or is that actually part of the noise? That's a problem that we cannot fix here or get the answer for here. Also, in terms of the depth, the depth direction when you do a profile, you could see that when you have the particle, you have an enrichment in phosphorus, as well as in magnesium. You have a depletion in silicon, but there's nothing that you can give in terms of information for the erbium. The counts are too low, the statistics are too low, this is buried in the background, there's no information that you can get. And also for the germanium, it appears to be fairly uniform, but it's also very noisy, so we don't know for sure if that's the case. So the question is, can we correlate these results with another technique? Can we get a bit more specific about quantification? And this is where the atom probe comes into place. We have basically, this is an SEM image of the fiber core with the electric opticals and the particles. That's part here, and you have the whole fiber here. So what we've done is that we prepared a lamella here, okay, and we cut it in different chunks, and with the FIB. So with the FIB, we actually prepared some samples and used the reflection system. And by doing so, we basically have samples that were taken from outside the fiber core, so in the matrix, and others that were inside. Okay, and you see the difference between these two regions where, so these two here were outside the fiber core, and you have a uniform distribution of the elements here, while in the fiber core you do have these precipitates or dielectric nanoparticles represented here especially by the magnesium. So now, what can we get in terms of the mass spectra? If we look at the matrix, we do have the silicon, the oxygen, with the phosphorus here, and different phosphorus oxide peaks here. If we look at the fiber core, we definitely clearly have the magnesium here, germanium here. We still do have the phosphorus oxide, but we still are lacking the erbium. Okay, I remind you that what we are after here for the information is what is not trivial. We are looking for the erbium, and the erbium right now is still not visible. So we need to apply better processing of our data to be able to find it, because it's there. Okay, so just to make sure that we did not miss anything, we've done some bright field imaging with the TEF, and we have found a broad range of dielectric nanoparticles. Okay, but even with the XCDS, we have confirmed the phosphorus, magnesium, and germanium information, but no information for the erbium. Okay, because the signal was really too weak. So this is where it's important for you to understand that when you do atom probe, part of it is specimen preparation, part of it is acquisition of the data, and there's another 50% remaining. This 50% remaining is the data processing. Okay, lots of the technique that you are using, once you've done your experiment, okay, it's pretty much you have 10% more of data processing and you're done. In atom probe, 50% of it is data processing, and this is where we're going to use now the data processing power to be able to find this erbium. For example, here we do have the ion maps, where you have the magnesium, the phosphorus, phosphorus oxide, and so on, and the germanium. The germanium seems to be also homogeneous, as the NanoSIMS has found it. But now we want to have information about the erbium. So if you look at the small particles that are less than 100 nanometer cube, there's no way for me to say there's erbium there because it's actually part of the background level. There's no way to differentiate it. However, if I take particles that are over 400 nanometer cube, then we do have here the clear pattern for erbium. Okay, and it matches the pattern that we have for all the different isotopes for erbium. Okay, so having the flexibility and the possibility to isolate these particles and do data processing on just these particles is extremely powerful. So we could even get information about the concentration. So now we can put some numbers in terms of how much erbium we have. However, I have to be, it would be a lie for me to tell you that the concentration measurement was absolutely great. We have an error bar of about 24% on the 0.1% erbium. Okay, so 24% error bar is high, but it's better than no measurement. Okay, so right now we are dealing with about 200 ppm of erbium in the whole glass. Okay, so it's extremely low. And we can finish here the story by using proximity histogram with the directed nanoparticles. So basically we have enclosed the particles with the magnesium interface. And what we are doing is that we are interrogating from outside the particles to interface to inside the particles. And what we could find is basically going from the matrix to the particle, we have 10-fold enrichment in phosphorus, 100-fold enrichment in magnesium, and we could also see this enrichment here, this strand going into erbium, going from the matrix to the particle. Okay. Again, look at the error bars. They are great. Okay, they are not very small like they are here for the magnesium. Okay. But we still do have a trend that you can notice. Okay, so now it's time for me to maybe talk about grain boundary analysis. That means that maybe I will have time to talk about the lithium ion battery. So, Kelvin, do you have a TKD system here? Do you have an EBSD system here?
We have EBSD. When the new phase is up and running, we hope to also have the TKD capability as well.
Okay, so that's going to be great for grain boundary, especially if you think about it. When you have a grain boundary, when you are doing analysis of a metal and you are after a grain boundary, this is where the interesting things are happening. And what happens is that when you prepare a wedge for the FIV, and then you go and do the sharpening, you see the grain here, but when you do the sharpening, the contrast is actually lost. So you won't be able to say if in this tip you do have the grain boundary or not. So if you have to actually shoot in the dark, basically, then you are wasting time, wasting money, and this is not what you want. So you can actually do the EBSD as you are milling your material, okay, and ensure that at any point of your milling, your tip does contain the grains, than your grain boundary. Okay? And most importantly, knowing that one of the limitations of atom probe, no matter which atom probe you are using, one of the limitations is that the specimen can fracture. You want to make sure that you reach your region of interest before your specimen fractures. So you want to make sure that your grain boundary, you don't put it at 500 nanometers down the tip. It has to be close to the apex so that you can actually minimize the time that you analyze and make sure that you reach the region of interest every time. So you can actually keep going and, for example, in this case, get the grain boundary closer to the apex and make sure that you can start analyzing it. Okay? So in this case here, we do have the SEM picture that we correlate with the atom probe reconstruction. And you have a system that contains some copper and aluminum oxide. So you have grain boundaries here. Okay. So this part here is sandwiched with the aluminum oxide. This one is sandwiched with copper. And with the TBSD, you can actually do some rotation and do some mapping in terms of the grains. So that information, such as the disorientation of the grains, could be obtained. And the complement